All right, let's take a look at example problem 3. Calculate the amount of work necessary for the reversible compression of 1 kilogram of steam from 10 bar to 5 bar. The expansion is to take place in a cylinder fitted with a weightless piston at the constant temperature of 400 degrees C. Okay, so temperature is constant and it's 400 degrees C, and we are compressing. We'll have reversible compression, and then here it says expansion, right? So it should be expansion because we're going from, so this should be expansion. I swear I took this from the book. Because our pressure is decreasing from 10 bar to 5 bar. All right, since temperature is constant, pressure is decreasing, expect our system to expand. Okay, so let me just take a note here. So in my initial state, we have a temperature, so T1 is 400 degrees C, and P1 is equal to 10 bar. And then in our final state, we still have a temperature of 400 degrees C, and our pressure is now 5 bars. Okay, and throughout this entire process, our mass is 1 kilogram. All right, so the first part, we're asked to calculate the work, all right? So we're calculate the work, and we're told that we're reversibly expanding our gas. So if I need to calculate the reversible work, so we're not told anything about shaft work, so we'll just assume that all the work is reversible PV boundary work. Then that's going to be the integral of negative PdV. Where again, it's important to keep, and I'm going to have some initial state 1, I'll call it, to some state 2. It's important to have this negative sign here because our sign convention is that when our system does work on the surroundings, that work is negative, and when work is done on our system, that's positive. So if I'm thinking of a piston cylinder and my system's expanding, all right, piston head's going up, that corresponds to my system doing work on the surroundings. Okay, so volume's expanding, dV is positive, so I need the negative sign to agree with my sign convention that work is negative. Okay, so just to bring out the negative sign, integral from my initial to final state, PdV. Now, in order to integrate this, I need to know how P depends on V. Right? I need to have a relationship for P with respect to V. Now, the last problem we just looked at, we were told to use our analytic equation, the truncated virial equation, right, which gave us a relationship for P with respect to V at constant T, and so we could numerically integrate. Okay, we're not given an analytic equation here, but that's okay. It's steam, so I know I have I've tabulated data in the steam tables, and so I can tabulate data, and in this case, numerically integrate. Okay, and we'll numerically integrate I'll do it in MATLAB, right, just so I can show that it's pretty straightforward and simple to do in MATLAB. So here's what I'm going to do. Right, the first thing I'm going to do is I'm going to confirm that I have superheated steam. So to do that, I'm going to the superheated steam tables, or I could go to saturated steam, but it doesn't really matter. Okay, and what I'm going to look at is at 10 bar. Yeah, so at 10 bar, saturation temperature is 179.89. So our temperature of 400 degrees is greater than Tsat, so we're superheated vapor. And if I were to go down to 5 bars, Tsat's 151.84, 400 degrees is still greater than that Tsat, so I'm going to have superheated vapor. Okay, so what I'm going to do is I'm going to collect data. I need to integrate P with respect to V. So what I'm going to collect is from the superheated steam tables, at 400 degrees C. Okay, I want to collect data for the relationship between P and V. Okay, So I'm going to collect data from P. It's going to be in bars, since the superheated steam tables are in bars. Then I'll get V, which will be in meters cubed per kilogram. Okay. Cool. Okay. Now, as I collect P, I'm going to integrate from my initial state to my final state. Okay. So the first data point I'm going to want is 10 bars. So I'll go at 10 bars, decreasing down to 5, just so that I get my order of integration correct. All right, because I'm going to integrate from my initial to my final state. All right, so let's collect data. So what does this look like? So we're at 400 degrees C, okay, and I said I'm going to start collecting data at 10 bar and work my way down. Okay, so at 400 degrees C, at 10 bar, okay, volume's 3066. Okay, and actually to make it easier on myself, so that's 10, 9, 8, and then it goes in increments of, so 9, 8, 7.5, 7, 6.5. All right, then they start to go in increments of half. 6, 5.5, and 5. Okay, so 9 is 3411. 8, 3843. 7.5 is 4102. 4102. Okay, 7, 4398. 6.5, 4739. 6, 5137. 5.5, 5608. And then 5, 6143. Uh, 6173. Okay. Now I see volumes increasing. Right. So again, we said our gas is going to be expanding, and so just want to take a note of the sign that I expect to make sure I get the order of integration correct and everything. All right, so we're expanding, so we know our work should be negative since our system's doing work on the surroundings. So our work should be negative, right? Just to make sure I get sign right. Now, when we compute this integral, okay, so I keep saying I like to work in SI units, so I make sure that my units are consistent. So V is in SI, so if I want P in SI, I would convert bars to Pascal, so I'd multiply by 1 times 10 to the 5. Integrate that, I'll get work in, the units will be joules per kilogram since I'm on a specific basis. Now, we have 1 kilogram, so then we can easily convert to joules if we wanted to, just have to multiply by 1. Okay, so let's get it on a specific basis, and then we could always multiply by 1 to get it on an extensive basis. All right, so let me create a new script. Okay. And so I'll store the mass to a variable just so we have it in kilograms. But what I'm going to need to do is I'm going to create a vector of P's and a vector of V's. Okay, so I'm going to create a vector of P's. Okay, and it went 10, 9, 8, 7, 6. Actually, 8, 7.5, 7.5, 7, 6.5, 6, 5.5, and 5. And then my vector of volumes. Okay. Hopefully I don't introduce any typos. .4739. Alright, and if you've never entered data like this in MATLAB, it's just bracket, a vector, and then each element. You can either just separate by a space or a comma. Here I have both. And if you're really not familiar, under home, there should be a new variable, right? I could always click new variable, and I could type up in, an Excel format if I wanted, and just click up here to name the variable. Okay. So let me delete that guy that it just thought I created. Okay, so now I have P and V. Okay, then to calculate the work, work is going to be equal to the negative integral of P with respect to V, from my initial to my final state. And so I'm going to use MATLAB's built-in function trap Z to do it. Okay, and so the way we'll use it is if I look in help, it says X then Y. All right, so X is my independent variable. All right, so in this case, that's V, right, the dV term. And then Y is my dependent variable, which in this case is P. So we're going to have V comma P. Okay. And that's just it. Okay, so let me save this. Oh, actually, this isn't going to be right. Okay, so what I need to do is, I said I want to make everything in SI units. So this is in bar. So then to convert P from bar to Pascal, I want P is P bar times 1e to the 5. Okay, cool. So now, let me run this. Okay, so running. Okay, so now I have P here, which is, so I took my pressure in bars and converted it to pascals. I get this. We get that our work is equal to negative 215,665, and this would be joules per kilogram, or divide by 1,000, negative 215.665 kilojoules per kilogram. Okay, and if I wanted W total, right, I would just take this and multiply it by our mass, which is 1 kilogram. Okay, cool. So that's W. So the amount of work, we've got it. Negative 215.665 kilojoules per kilogram. And again, sign convention, it's negative. That means our system is doing work. That's what we expect. So that's great. That means I, properly integrated, right? So I properly set this up to integrate by sorting from my initial to my final state. Okay. If you wanted to flip it, right, then you would just, just as a note, right, if I were to flip the order, that's the positive integral from, now it's my final state to my initial state, PDV, right, from calculus. Okay. But I'm going to erase that just so I don't confuse you. But So what would have happened is if I would have organized the data in the other way, I just would have had an opposite sign, which I could have flipped by negating. All right, so that's W, and now we want to calculate Q. Okay, so the key is in B. Okay, my first law of balance is that delta U is equal to Q plus W, where U is going to be U2 minus U1. Now, when I look at my initial and final state, I know the temperature and pressure of my initial and final state. Right, I have a superheated vapor in both states. So single component, single phase, states completely specified. I can look up U2 and U1 in my superheated steam tables. Okay. So I'm going to have that Q is equal to U2 minus U1 minus W. Okay. So let's look up U2 and U1. Okay, so for my superheated steam tables, so at 5 bar and 400 degrees C, U is 2963.6. And that's kilojoules per kilogram. All right, so part of the nice reason for leaving W in kilojoules per kilogram is that's the same units as U, so I won't need to worry about converting anything. Okay, so I'm looking at 400 degrees C and 10 bars. That's down here. 2957.8. That's kilojoules per kilogram. Okay. So Q then is equal to, let me go to MATLAB and let me enter U2. And so let me get W in kilojoules per kilogram. That was W divided by 1,000. So U2, 2963.6. U1, 2957.8. So the Q, which is going to be in kilojoules per kilogram, will be equal to U2 minus U1 minus W, and I'm going to use the value in kilojoules per kilogram to get a Q in kilojoules per kilogram since my U's are in kilojoules per kilogram. All right, so Q then is 221. This is a positive 221. 221.4650, and that's kilojoules per kilogram. All right, and my answer makes sense, all right, because my system's expanding, so work is negative, work is being done by my system on the surroundings. Q is positive because in order to get my fluid to expand, I need to add heat. All right, cool. Right, and notice the Q and W are not exactly the same. Right, the difference is equal to that difference in internal energy. Okay, cool. Hope that helps.